Okay, I'm going to introduce you guys some new functions. This is the first one. This is called the unit step function. This is also called the Heaviside function. All right, Heaviside is just the name of the person. It's not because this side is heavier, so that's why it's down below here. Anyway, anything before 0, you see the function value is 0. Anything after 0, the function value is 1. Right, and we'll write it as u of t, which is 0 or 1, depending on the t values. Right, and the second one right here, we'll just pretty much take the first one and then shift it to the right, a unit. So anything before a will be 0, anything after a will be 1. And we write it as u of t minus a. Once again, this is the definition. You know they are the piecewise functions, right? Last one, this is called the rectangular window function. Sometimes you just care about a and b to be 1, right? So any values t in between of a and b will make it equal to 1. Anything else, they will be 0. So otherwise we get 0. That's how I wanted to put it down. And the notation for the rectangular window function is capital pi a comma b and of t. And this right here, it's the same as this right here, u of t minus a and then minus u of t minus b. And you can just pretty much play around with this equation and you'll see how this equation is the same as that. Anyway, right here, I would like to show you guys the Laplace transform of u of t minus a. I'm not going to do this one because this right here is pretty much the function 1. And remember, the Laplace transform is the integral from 0 to infinity. So we don't look at anything before 0 anyway, right? So if you want to do the Laplace transform of u of t, you just get 1 over s because that's the same as Laplace transform of 1. This, which is this picture right here, this is not exactly 1 because we are missing this part. So let's take a look of what this is going to be. This is a new function, so let's go ahead and use the definition. That will be the best bet. So the Laplace transform of this is equal to the integral from 0 to infinity e to the negative st times this, right? u of t minus a dt. This is what we have. Okay, take a look of this picture. When we have 0 to infinity, technically it's from here all the way to infinity, right? But this part is missing. We don't have any value right here, just 0, right? This right here, it's the same as saying the integral, we just care about the area pretty much, right? If you think about it, this in terms of area. We just care about starting from a to infinity, right? And remember, when we have jumps like this, it's okay, right? For this kind of Laplace transform business. So even though it's not defined at a, but once again, it's okay. Anyway, this is the same as saying from a to infinity, and then we still have the e to the negative st. And then if we are just talking about from a to infinity, the value of this function is just 1. So we just say this is 1, and then we have dt, like that, right? All right, now let's finish this up. This is just going to be the limit. So let me just do this legitimately. The limit as n goes to infinity, and then this is the integral from a to n, and then we have e to the negative st dt, right? And then this is the limit as capital N goes to infinity, and then we integrate this real quick, which is going to be negative 1 over s, and then we have that e to the negative st, and then we're going to plug in numbers, right, with a and n. So t goes from a to t goes to n, like that. And then do it real quick. This is going to be the limit as n goes to infinity. And then plugging n first, we get negative 1 over s, e to the negative s times n. And then this is the first term, and then you do minus that, which is minus 1 over s again, and then you have e to the negative s, and then you plug in a into here, so you have s a. This is my a, this is not 9. Anyway, this is what we have. Well, you know the deal, we have done this a few times. You want this term to be 0. To do so, you just have to set, right, I'll just put down, we need to set that s has to be greater than 0, right? So this right here, you remember you want it to be 0, so you set this to be greater than 0. And it will be 0, right? So you pretty much will have 0 right here, and then minus, let me just put it down, minus minus minus, which is become plus, and then you have the 1 over s, and then e to the negative sa, and the 0 doesn't matter. So finally, when you do the Laplace transform of this, you just get pretty much 1. Let me just write it down right here. Do all that, and then you get e to the negative sa, right? Sa over s, right? And this is the answer for that. Okay? And real quick, I'll do this in blue. Let's do the Laplace transform of the pi a b. So right here, let me just draw like a box. Let's look at the Laplace transform of pi a b of t. Well, I don't need to use the definition of the Laplace transform, but this right here, right? Because this right here is just going to be the Laplace transform. Inside, it's the same as saying u of t minus a, and then minus u of t minus b, u of t minus b, like that. And do we know the answer right here? Yes, we do. It's that, right? And you see, when you have t minus a, you have e to the negative sa and over s. So this is going to give us e to the negative sa. Let me just put down negative sa and then over s. And then minus, when you have minus b right here, right? So t minus b, you get e to the negative sb over s. All in all, you can put them together, which is e to the negative sa minus e to the negative sb all over s. This is it. That's it too.